Hi everyone, welcome to the Buidl Radio podcast. We're a spin-off of Ukrainian blockchain dev community Buidl in UA. As Ukrainians are widely distributed nowadays throughout the world, we continue our deeds remotely and creating this podcast. This is episode number 3, recorded as of mid-December 2022. My name is Polina Aladina and my co-host Andrei Sobol. Welcome.
Hi everyone. Today we talk with Toghrul Maharramov. Toghrul is a protocol designer in Scroll, and we will talk about ZK-based layer 2s. Like, why I invite Toghrul from Scroll, not someone from Metro Labs? Because I hope in this podcast we will have time to talk with the technical people from Metro Labs, but today I want conversation about ZK-based layer 2 in general, so I want someone external, because if one guy from Metro Labs will ask questions, another guy from Metro Labs will provide response, it will be a conversation about ZkSync, not about layer 2 in general. So I want some level of neutrality, and I just say hello to Toghrul. Hi.
Hello.
Before we start, can you please talk a little bit about your experience, about your expertise?
I think expertise is a bit of a strong word. I mainly just shitpost on Twitter. That's my job title. But I do research at Scroll. I mostly focus on decentralization, incentives, bridge design, so mostly protocol stuff. I don't really touch cryptography because I'm not a cryptographer by trade, and I also don't really know cryptography that well to basically work on it. And my main priority at Scroll is to make sure that the protocol is the protocol on the bridge level is as efficient as possible and also as user-friendly as possible.
We don't need to ask you about cryptography, right?
Yeah, I'd rather avoid it.
Alright, so let's do straight off deep dive. Can you tell us about what is the biggest problem about making a zero-knowledge EVM? Like, what's the problem there? Why can't you just easily create an EVM?
The problem is that when EVM was designed, snarks weren't really a thing. Snarks didn't exist at all back then. And nobody had thought about making it zero-knowledge friendly because it wasn't really a thing when it was designed. And so there are a lot of decisions that were made back then that basically have come back to bite us in the ass.
Sorry to interrupt. Can you define zero-knowledge friendly in this context?
So zero-knowledge friendly is essentially a protocol, or in this case a virtual machine, that can be easily implemented inside the circuit. So essentially, instead of using a lot of constraints or a lot of gates to define a single operation inside that particular function, you can use quite a few, and that affects the prover. So essentially, if you use a lot of constraints to define a single operation, the proving time is going to be dramatically higher than it's, say, in an operation that requires just a handful of constraints.
So EVM used to be not friendly for zero-knowledge proofs, and
unfortunately, it still isn't zero-knowledge friendly.
It hasn't
Nothing
changed much. Yeah.
Yeah, I think we're stuck with it forever. And so the goal, you can approach ZkEVMs in different ways. So one is ZkSync approach, where you just assume that from the ground up that EVM is not the best VM to implement, and so you aim to support as much of its functionality as possible without actually emulating it. And then there's Scroll approach, where we actually implement EVM opcode by opcode inside the circuit. And essentially what that allows us to do is we can support all the existing smart contracts that have been compiled to EVM, that the EVM bytecode, and you can just copy and paste it from Ethereum, deploy it on Scroll, and it'll work out of the box. There are other reasons why we think it's the best approach, but it's a long discussion, and I'm going to bore everyone with it, so I'm just going to avoid talking about it. And back to why ZkEVMs are difficult to build. So those operations that were basically not zero-knowledge friendly. So, for example, a hashing function. Inside EVM, everything is hashed using ketchup. But ketchup isn't a zero-knowledge friendly hash function per se, so it requires a lot of gates in order to be implemented in circuit, and therefore it's super slow to prove in circuit. It's obviously fantastic when you're executing it outside the circuit because in CPU it's super fast, whatever, but for our specific use case, it's not great. And there are a lot of operations like that that weren't built with zero-knowledge proofs in mind, and therefore are quite inefficient, basically, to implement in circuit.
You mean pairing or some others opcodes?
Oh, but even the fact that Ethereum's word size is 32 bytes or 256 bits, a field element is usually smaller than that, so it doesn't fit inside that element. So you have to basically split the word into multiple field elements. Sorry, not field elements, scalars. Yeah.
You said that there is crypto primitives it's hard to build inside ZkEVM, but maybe some other opcodes, for example, like memory co-oping or what can be complex also.
Oh, for example, storage, the same, because storage uses storage in Ethereum is implemented in a tree-like form. They specifically use Merkle-Patricia trees. It's not required. You can use other. For example, we use Merkle trees, but it's the same. The problem is the same, essentially, because on every layer you have to hash it, and usually hash functions are not very. Even if you use Poseidon or something more zero-knowledge friendly than Ketchuk, it's still basically not as efficient as you can get it without the tree structure. And from the implementation perspective, that is not what I would call optimal.
And how this topic ZkEVM related to the rollups and Validium? Why we need it? Can we build rollup without it?
Yes, you can build a rollup with anything as long as you have defined a state transition function. In an optimistic rollup, you have to have a way to basically create a fraud-proof mechanism for that state transition function. In zero-knowledge proofs, you just have to have a way to circuitize it. And so as long as you can circuitize your state transition function, you can do whatever you want with it. There's a project that is building Solana VM on top of an optimistic rollups, Solana VM optimistic rollup on top of Celestia. And so essentially your imagination is the limit, and also your constraints, because let's say if you implement something that is very expensive to prove, you might end up with a situation where a single block takes days to prove. So it's a matter of what your priorities are and what your design goals are.
Right, so can you maybe elaborate a little bit more on what's the difference between different rollups that exist? What's the difference between Scroll, ZkSync, Validium mentioned by Andrea as well? Are they good or bad?
I don't, fortunately or unfortunately, depending on if you ask me as a rollup maxi, then it's fortunately. If you ask me as an employee of Scroll, unfortunately, there's no such thing as a bad rollup. Every single solution has their own trade-off and has their own benefits. So if we go back to ZkEVMs, for example, essentially you can see it as a linear scale. You can, on the left, you can have a solution which is the most compatible with Ethereum, and on the right, you can have the solution that is most efficient in terms of proving. And so essentially different projects can take different approaches and how to, depending on what priorities they set. For example, ZkSync's approach is to be as efficient as possible while being relatively compatible with Ethereum, whereas Scroll's approach, for example, is completely the opposite. We assume that proving will not matter long term, but we want to be as compatible. We want to maximize compatibility with Ethereum. And so you have this landscape where you can fit within this scale and design different ZkEVMs to tackle different philosophies or your design goals. And when you asked about validiums are not actually rollups. So what differentiates a validium from a rollup is data availability. So in a rollup, the data availability has to be the data has to be published on Ethereum or whatever base layer you use. Whereas a validium, you can have some external data provider that basically stores the data and provides some guarantees under some assumptions that the data can be retrievable at some point in the future.
Right, like how do you think, just in general, maybe layer 2 solutions Rollup partially fit into like broader landscape of blockchain and crypto development? In general, like what things do they add up to?
I see rollups as the most optimal way to scale things in blockchains. So if you assume that an approach of just having one monolithic chain is unviable because at some point you're going to run into basically hardware constraints, or your hardware requirements are going to be so high that only a handful of people in the world would be able to run the full nodes. We need to basically scale by sharding the chain. By the way, I'm not using the term sharding in its technical form. I'm just describing a way of basically running different chains in parallel. So you have to find a way of doing it. And out of all the existing solutions, rollups are the most secure way from the perspective of how many assumptions on top of the base layer you need to add in order for it to operate securely. So essentially, for example, if you operate a sidechain usually requires another honest majority assumption on top of your already existing honest majority assumption. Whereas in a rollup, as long as you properly implemented rollups, because if you look at all the existing rollups, they're not actually rollups because they have they take some trade-offs while they're being optimized and also being test run essentially in a live setting. But at some point, all of them are going to remove what Vitalik calls training wheels and going to become actual real rollups. And in a real rollup, the only assumption that you have is that the state transition enforcement mechanism is properly implemented, is secure essentially. So in optimistic rollups, that means that there is one honest full node, the rollup full node that can challenge a commitment. Whereas for a zero-knowledge rollup, you assume that the zero-knowledge proof system that is used by that particular rollup is secure and safe, either from the implementational perspective or from the theoretical perspective. Actually, both, but yeah, sorry.
Do we have some additional requirements, security assumptions when we build Rollup is just compared to the just straight layer 1 chain?
There are arguments on what makes a rollup, but I would say that in my opinion, a rollup should only have this one assumption that I described. If you add any more assumptions on top of it, it's no longer a rollup. For example, Validium is still an L2, but it's not a rollup because it doesn't have data availability on-chain, which means that you have to assume that the place where the data is stored can guarantee that it'll make that data available at some point in the future, which means you need to make additional assumptions.
Okay. You mentioned that rollups is like the most optimal way for scale blockchains. In current setup, in the current Ethereum, do we have some like upper bound limitations for scaling Ethereum with the rollup? Can we say that we can like scale Ethereum 10 times or 100 times? How we can calculate it, and what the upper bound will be in this case?
If you assume that there are no other bottlenecks, the fundamental limit of how much you can scale Ethereum through rollups is data availability capacity on Ethereum. So essentially how much data Ethereum can store per block or per second, depends on how you want to define it. And I made some rough calculation. Obviously, I just disregarded that there are other bottlenecks. So, for example, the way you control the state, proving, etc., just assume that they don't exist for a moment. I wish it was a real world, but no, it's just an imaginary faux process for a second. I think I came to a conclusion that we can push up to like 80,000 TPS, or in between 80,000 and 100,000 TPS on chain, without resorting to Validiums or ZK porters or something like that, where you have data off-chain.
It means that it will be like, not like one rollup with this TPS, it will be like something like 100 rollups with like strongly divided TPS per chain. How people will use it and how people will move liquidity between all of this rollup? Do we need like something like layer 2's bridges between all of these chains, or like layer 2 messaging system, and how it will work for the user perspective and the user experience perspective?
I think from if we're talking about tokens specifically, I think we already have an ideal solution for that. It's called repayment protocol, so something like Connext or Seller. It's as long as the liquidity is there, is satisfied. It's basically the most trust minimized way you can transact between two rollups. And if we're talking about arbitrary messaging, there are a few approaches. So, for example, there was this paper by Geometry. I think it was Geometry, by Geometry, called Suez, which basically allowed you to bridge from one L2 to another, or they specifically created for L3s, but you can also do it for an L2, as long as you can prove that the data was included and finalized on the L1. So instead of waiting for the validity proof to be submitted, you just need to wait for the data to be submitted, because you can just prove that the data is correct yourself. You don't need to wait for the validity proof to be finalized. So there are definitely another option is using optimistic bridges, something like Nomad, for example. But yeah, I think for arbitrary messaging, it's a bit more difficult. Whereas for token bridging, I think for the majority of the users, unless you're trying to move like $1 billion at once, it shouldn't be an issue.
Alrighty. So you're working in Scroll right now, and can you maybe elaborate a little bit? What are the biggest challenges that you have right now going forward with the Rollup technology in general? Maybe with crypto, if you can talk a little bit more about that, but maybe just for yourself specifically.
If we're talking specifically about rollups, I think that I wouldn't call it an issue, but it's just like the most difficult thing to implement from my perspective is how do you decentralize rollups? Because it's paradoxic in a sense that it's much easier to decentralize an L1 than an L2, because your goal as an L2 is to minimize the overhead as much as possible, and you could slap a consensus on top of it, but you're already paying Ethereum for a consensus, so that's just an additional overhead that you don't need for the rollup to function, but you need it to decentralize. And so the question is, where is the middle ground between the best UX that you can offer and the least overhead that you can add? And from my perspective, that's the question that none of us have really answered at this point, and there's still quite a lot of discussions on what's the most optimal way to go about it. But if we're talking about crypto in general, I think my biggest concern going forward is censorship resistance and how you fight it. There are obviously theoretical solutions such as PBS plus CR list, etc., but there are still a few things that we haven't really figured out. And from the Tornado Cash debacle and the after effects of it, like OFAC, etc., I think it's necessary for us to pay more attention to that side of crypto and not just how to scale. Because if you can scale a protocol that can arbitrarily censor anyone, there's no point in that throughput. You just essentially got yourself another AWS or whatever, just a random database.
Yeah, well, that's true. So for decentralizing a rollup, like why would you actually decentralize a rollup if you have a presumption that security goes in the verification? So it's basically decentralizing the storage of it, right?
So in a rollup, you don't need decentralization from security perspective because you retain all the security from the underlying base layer. It's more of a UX thing, so you would decentralize to improve the UX because let's say if you rely on one sequencer and the sequencer refuses to include an Oracle update into a batch for one reason or another, and you can force the inclusion after a certain period of time, but let's say within that period of time, the volatility is great and the users that could have been otherwise liquidated, aren't liquidated. So the protocol, the DApp that was dependent on that Oracle essentially becomes under-collateralized or unhealthy for one reason or another. There are a lot of situations that you can come up with that rely on this certain assumption. So decentralization is important from that perspective because the more decentralized the rollup is, the harder it is for the rollup sequencers or full nodes, whatever you want to call them, to censor the users. Obviously, you have this fallback in a complete, the worst case, in the nuclear option of forcing it through an L1, but ideally, it should be a nuclear option that is never used. It's just there in the back of your mind that you can never lose your money or have the money frozen because you can always force. I think from the UX perspective, it's important to decentralize, but it's not a priority because I think, at least in the beginning, for every rollup, the priority is the security. Because you can have a decentralized rollup, but let's say if the validating bridge is compromised or something else is compromised that leads to funds being frozen or funds being stolen, that's it, basically. Your rollup is done, nobody's going to use it.
So you're seeing that only reason why we need decentralization in rollup is just user experience. How it relates to the censorship resistant? Because in my opinion, it's much simpler to provide some censorship resistant protocols with decentralization. Because if you have centralized sequencer, first of all, you have strong incentives to censor transaction. Because a lot of people around this sequencer will say, please censor this one and this one and this one. And you need somehow to resist this pressure. What about censorship resistance and how it relates to the decentralization?
One of the requirements of an off-chain protocol to be classified, for an off-chain protocol to be classified as a rollup, is censorship resistant. So it has to retain the censorship resistance guarantees of the underlying base layer. So let's assume that we're talking about a rollup deployed on top of Ethereum. Even if the sequencer attempts to censor, there should be a way for the user to force the transaction to an L2. So in rollups, the most obvious solution that you would have is Arbitrum, for example, refers to as an inbox. So essentially, there's in the L1 contract, the validating bridge, the user can attach the transaction to the bridge, and it sets a certain timer. Let's say, I don't know, you can set a timer of 24 hours. And if that transaction is not consumed from the inbox and included into one of the batches that is submitted by the sequencer within 24 hours, the validating bridge no longer accepts any batches that don't include that transaction. So as a nuclear option, you can always do that and essentially retain the censorship resistance properties of Ethereum, because as long as Ethereum is not censoring your transaction, it'll be eventually included.
But by the way, can we make layer 2 more censorship resistant than layer 1? Do you have some construction in your mind how you can implement some different protocols where you can complicate the way how you can censor some transaction from some user?
You could potentially use some form of threshold encryption, or, for example, there are some other methods. I think fair ordering can make censorship much more difficult. But at the end of the day, is it worth implementing those solutions if they make your protocol if they create an enormous overhead to the protocol that aims to minimize overhead. So essentially, for example, if you use Sharderization and encrypt transactions when they're batched and then decrypt them at some point in the future, you have to prove that, for example, for Zk-rollups, you would have to prove the decryption correctness in circuit when you're proving the correctness of the batch. And we're all fighting to minimize the sizes of our circuits, and just adding additional steps that are non-trivial and are actually quite complex just doesn't make sense at this point. Maybe in the future, once the proof systems are more optimized and we don't really care about the proving times that much, and we can increase the circuit size, then it might make sense. But at the moment, I just don't feel like it makes sense at all to do that.
You mentioned fair ordering. I read paper about fair ordering, but can you please explain a little bit to our listeners what does it mean? Can you please explain a little bit the concept of fair ordering?
So fair ordering is essentially, and bear in mind, not everyone agrees that it's even possible. So for example, Phil Dyan from Flashbots thinks that it's just a way to minimize basically arbitrary insertions of transactions, but it doesn't actually eliminate it completely. And so essentially fair ordering is this concept that you can guarantee inclusion into the block on a first-come, first-served basis. So essentially, it's a FIFO stack where the first transaction that comes in, that is received by the majority of the nodes, is the one that is going to be included in the block. I'm not going to go into the details of how it's actually implemented, but the core idea is that the majority of the nodes receive this transaction first, and it's going to be included in the block first.
What about time lock encryption? What do you think? Is it possible to use it for censorship resistant protocols in near future, or it will be too hard to prove on zero knowledge?
Difficult. Yeah, I think it doesn't make sense. At least when you're referring to time lock encryption, are you referring to actual time lock puzzles that are used to encrypt, or because when I was referring to Sharderization can be under certain assumptions can be defined as time lock as well, because you need a threshold of consensus participants to decrypt the transaction at some point in the future. But obviously, something like time lock encryption can't be gamed the way Sharderization can, because there are no honesty assumptions. As soon as you solve the puzzle, you can actually decrypt it. But
no, I mean real VDF. I'm really VDF.
Okay. Yeah, no. I don't think that's going to be. I like the idea. I think it's an interesting idea, but I think it's a pipe dream at this point to make it viable. Even not on rollups, I think even on L1s, that would be a pipe dream to make it viable.
Do you know that if someone implemented after 1 year, it will be it will be the 1 minute video where Toghrul says that it's impossible. Nobody will implement it. It's.
Oh no, I'm not saying it's impossible. I'm just saying that it's not really viable at the moment. Maybe at some point in the future it is, but I think using VDFs for time lock encryption is something that I would consider fantasy at the moment for a high throughput efficient protocol.
I have a different, a little bit question. So, are there any other use cases for zero knowledge proofs except for layer 2s? Well, I know there is a blockchain that uses zero knowledge proofs, but maybe there are more non-crypto related things that you can do with that. And yeah, are they used somewhere, or how do they use them, and so on?
Yeah, of course. Just as a preface, zero knowledge proofs inside zero knowledge rollups. Well, you would assume that zero knowledge proofs are something that is privacy preserving. But modern zero knowledge proofs have this property that is called succinctness, which means that essentially it takes less time to verify the proof than to re-execute the computation that it is proving. So essentially, you can imagine me proving to you some massive computation that I've done on my computer, and you, instead of redoing all that computation, just verifying that one small proof and getting quite strong guarantees that it's actually been done correctly. And essentially, this is the reason why zero-knowledge rollups are called zero-knowledge rollups, because of that property. They're not actually privacy-preserving, and a lot of people get this confused, and I think that's the peculiarity of the name, because we've I think it was Vitalik who came up with zero-knowledge rollups name first, and it's just stuck. Starknet tried to push for validity rollups, but I don't like that name, and I don't think it's stuck with anyone. With regards to what are the other use cases of zero-knowledge proofs, the main use case is privacy preservation. That's the reason why they were created in 1983. So essentially, you could prove that you know something without revealing any information about what you know. For example, or let's say you're going to buy some alcoholic drinks, and instead of them asking for your ID, you can submit a zero-knowledge proof saying that you're above 18 without revealing your actual age or your ID or what your name is, etc., etc. And I think it's quite a powerful tool, especially in the current world where there's a lot of surveillance and a lot of things are happening because for the last 20, 15 years, none of us really cared about securing our data, and zero-knowledge proofs help with that a lot. They allow us to interact with one another without divulging the information, and trust one another without actually divulging information, some sensitive information that we wouldn't otherwise want to reveal.
Yeah, I still got a feeling that if not for crypto and the needing for layer 1 to scale, like Ethereum needed to scale, so like rollups started to exist with time, because I remember where there were no possibilities to scale Ethereum, it was only talks, and Plasma started to show up a little bit. But then there's like this huge like community around general zero-knowledge proofs and how could they apply to Ethereum with rollups or something else. Like, it seems that if not for the cryptocurrency, the zero-knowledge proofs wouldn't actually make it through. So there is more of a question, is there any usage where it's completely not related to cryptocurrency as is, where they actually utilize zero-knowledge proofs somehow? Because, yeah, from my perspective, I learned a little bit of zero-knowledge proofs in university back in like 2011 or so. And yeah, so I can actually see how like more and more things are done there. But is there any other sphere that is not cryptocurrency that actually uses those?
I'm not sure if anybody uses them at the moment, but also bear in mind that like until I would say 2014, when Zcash started, the Zcash paper was published, I think it was 2013 actually. Mm-hmm. Zero-knowledge proofs weren't really efficient, so the proving was very slow, the proof sizes were massive, the verification was very slow, and the progress that we made in the last decade is, to some degree, mind-boggling, because even in 2018, implementing EVM inside the circuit would have, if you would have gone to one of DEF CONs and it would have gone on stage and told that to others, they would have just looked at you and thought you're just insane. So the progress that zero-knowledge proof systems have gone through in the last decade, I think that they've almost reached the point where they're viable to be used in a lot of different use applications outside blockchains that wasn't really possible before, either because the proofs were too big, or the prover times were too slow, or the verification times were too slow. But there were always a lot of trade-offs involved, whereas right now, I can see zero-knowledge proofs being used on a mass scale outside blockchains for certain applications.
Are there a lot of trade-offs that you actually have to do with zero knowledge? Like, are there things that you definitely cannot be solved as of now? Like, you cannot easily put them in zero knowledge proofs because as you're talking, we can use it in privacy here and there. Are there data that you cannot prove easily at all? Or is it just you can anyhow, somehow, any information that you own without revealing, you can prove it to someone? What kind of limitations exist there?
So you can't, for example, prove the existence of so let's say you can't prove that you are of a certain age to me if I don't have a certain commitment that contains the commitment to your age. So essentially, if you just out of the blue send me a zero knowledge proof saying that you're over 18, I have no way of verifying it because there's no commitment to your age. So you can just make up a number and lie to me. So there must be some shared commitment in a lot of use cases. Obviously, not every single use case. For example, if you're just proving that you correctly added 1 + 1 and got 2, I don't really need to know any information aside from the proof itself. But for certain use cases, you need that commitment to the data. So, for example, in Zcash, you can't actually spend your coins if you don't provide the commitment to the coin tree that contains all the coins in them, because you can just make up an arbitrary coin tree otherwise and just say, oh yeah, I have actually spent 1 billion Zcash tokens without actually proving that they were real and you haven't made them up.
Right. So if I were in the United States and I need to prove somehow that I'm over 21 years old to buy some alcohol, like how would that process actually look like? What would be the commitment here? So
I would assume that the US government, assuming that you are a US citizen or have some sort of a US ID, I would assume that there is some database that contains the Merkle tree or some other form of basically data storage that allows you to easily commit to a lot of data. And essentially every single vendor would have the state root, which contains all, let's say you construct a tree and every single leaf is an age of a certain person and their ID number or whatever else. And essentially I would construct the Merkle tree and as a US government and send the root to that Merkle tree to every single vendor. And in that case, as long as they have that root, you can prove that your ID is included in that root and your age is actually above the legal age of drinking in that state. And so essentially you just need that commitment. And there can be other ways you could do it, but this is the most straightforward way you can do it.
Coming back to our blockchain things, you mentioned that there is the Rollups. It's an optimal way for scaling blockchains. But what? Let's talk a little bit about other way. Let's talk about a little bit about what we called inside the blockchain sharding approach. It's not when people outside of the blockchain sphere heard sharding, they think about sharded database, but it's not about sharded database. It's about different chains where you have different committees. Why do you think is this sharding approach with was implemented by Parity and by Cosmos? Is it viable? Why you think only these complex things like Rollup can scale blockchain? Why not just simple sharding where you just have different committees and that's it?
There are obviously different approaches and depending on what your priorities are. So for example, Cosmos has this vision of sovereignty and self-sovereign chains. And essentially in that case, rollups in their classic form don't really make sense. So you can have something like sovereign rollups, but they have different assumptions and they just essentially just share the name with what I would refer to as classic rollups, but they don't really have a lot of in common with them. And when it comes to what you refer to as sharding, and essentially like your classic sharding, because you can have something like Danksharding where you don't actually have committees, you just have one proposer, but the data that is propagated is sharded. The difficulty with having committees and is that, well, you assume that you're sharing trust. The trust is distributed between different shards. It's not the same as the overall security of the underlying. You can refer to it as a beacon chain or base layer, whatever you want. Because let's say you have 1,000 validators on the beacon chain, but then you assign only 32 validators to each shard. The probability of a single shard being dishonest is much higher than the probability of the beacon chain being dishonest. So you still, despite the fact there might be share economics, you can, for example, slash the committee of a shard that makes an invalid block proposal, or some other ways you can do it, but you still have to rely on suboptimal trust assumptions, suboptimal security guarantees, whereas with rollups you don't have any of that. You just have you just need to assume that the proof system being used is secure, and that's it.
But like in Polkadot, they have like interesting approach how they avoid.
I knew that you would mention Polkadot.
Yeah, yeah. So what you explained before, it was more or less related to the adaptive corruption. Adaptive corruption strategy where you just choose some particular shard and say, I want like validators exactly from this shard. I like give some money, additional money to this validator and ask him to like, for example, sign the different state transition. But like in the Polkadot, they have like interesting approach where they, if something went wrong in some particular shards, they escalate it, and the bigger amount of validator, in the end, like 100% of validators, they go to these particular shards and they become validator of these particular shards. Of course, it's like, in the end, it's like, it's escalated to the, like, let's call it Solana approach, where you have like one big chain. But in normal case scenario, where every validator assume that if something went wrong, every other validator will join this network, it's like protect you from this behavior.
So I would say that to some degree, Polkadot can be seen as a proto-rollup chain. Their approach to sharding is almost what I would classify a rollup, but not completely. So yeah, Polkadot is different in the way they construct things, and I think that sharding is rollup-like, but it's not quite. And I think that not quite makes a difference. So for example, what's his name? In Polkadot, you need to assume that every single parachain has at least one honest. I forgot how they call them. The validators that they assign to each chain, to each parachain, whatever they're called. You have to have at least one honest one for censorship resistance, whereas in a rollup, you don't need to make that assumption because you just assume that the underlying base layer is honest. And so there are sort of minor differences, but Polkadot is definitely a way to basically rollupize sharding. Let's call it that way.
You mentioned Danksharding and Proto-Danksharding, I think. And what is Danksharding? What is Proto-Danksharding, and how it will increase the throughput of the rollups?
So, firstly, just before, Danksharding was an idea that an Ethereum Foundation researcher named Dankshard Weiss came up with. And by the way, a lot of people think that he called it after him, say if it wasn't him. It was actually Vitalik who called it Danksharding. So, yeah. And the idea behind Danksharding is what Dankrad refers to as tight integration between the beacon chain and the shard chain, where instead of having this multiple committees that each produce their own block, and then the beacon chain combines them all into one big mega block, or whatever you want to call it. There's none of that, or it combines the commitment, not the blocks themselves. There's none of that. So because we assume that MEV has a centralizing effect, and we assume that basically PBS is inevitable, so proposal builder separation, wherein there's a handful of builders who construct the blocks to extract as much MEV as possible, and each validator can be a proposer, and so they can just choose the builder with the most that pays the most money to them to include their block, and then they include that block. So if we rely that on the fact that this assumption is true, which at least for now it is true, we and the builders are quite computationally expensive to run. We can also assign other duties to them. So in this case, we assign them the task of building these massive blocks, constructing KZG commitments for them, so the cryptographic commitments to every single shard, let's call it that way. They're called block transactions in Ethereum, but let's refer to them as shards. And then disseminating them to different peers in the network. And this allows us to basically have no additional trust assumptions in terms of how the blocks are produced. And basically, you just need to assume that all the nodes, and with data availability sampling, you also have that work, which allows you to check whether enough data is actually available to be convinced that with high likelihood all the data is going to be available. And so it allows you to have quite an efficient construction where you can produce large blocks without actually requiring every node in the network to store them, and without resorting to committee-based sharding.
Yeah, but what about trusted setup? For KZG, we need trusted setup, right? So we need one more huge additional assumption, right?
I wouldn't call it huge, because as with every single other modern trusted setup, you need just one honest contributor to the setup to be assured that it's secure. And I think, considering that it's going to be likely that there are going to be thousands, if not tens of thousands of people contributing to the setup, I think it's very likely that there's going to be at least one person who's being honest and acting in an honest manner. Of course, yeah, it is an additional assumption, but I think because of the number of participants, it doesn't really matter. And also, if you don't trust it, the KZG ceremony is open to everyone. If you don't want to trust anyone at all, you can participate in it and contribute yourself. Then you don't have to trust anybody else, as long as you trust yourself.
Yeah, but this, it will be option only for the people who right now understand what Ethereum is, have deep understanding about Ethereum, because they understand what is KZG commitment, what is Danksharding, what is all of these things related to it, and they understand the importance of the trusted ceremony as they want to participate. But this argument will be totally invalid for the people who will use Ethereum after 10 years. Because, after 10 years, you cannot say to a new user, please participate to the ceremony which happened 10 years ago. This guy should believe that there is only more than zero honest participants to this ceremony, but they cannot prove it. They cannot experience it. They cannot participate to the ceremony because it's happened 10 years ago.
There are two answers to this. I don't think in 10 years we'll still be using KCG with trusted setup. And two, I think that in this case, it's very transparent. You have the data. If you really want to, you can download all the blocks that use KCG commitments and recompute the KCG commitments and see if they're actually correct or not. And that way you can basically figure out whether whether the KCG commitments were faked or not. So you don't really have to. It's not a situation where that is similar to, let's say, if Zcash's proof system was broken. That way you can create fake money out of thin air and nobody will find out. In this case, if you fuck around, essentially you'll find out eventually, because people can just recompute the KCG commitment and see what the commitment whether it matches your commitment or not.
By the way, there is a bug. It was a bug in Zcash when people can print money.
Yeah, I remember that one.
Yeah, but I think this is a topic for other podcasts, for other episodes, because a lot of weird things happened in early zero knowledge adoption or whatever.
Yeah, for sure. Yeah, but what I'm saying is that in this case, it doesn't really matter, because you can always just recheck it for yourself, and it's quite transparent.
All right, so recently you wrote a tweet, quote, "As promised, here's the Ethereum glossary written entirely by ChatGPT. Don't blame me for errors, I didn't author this, lol," end of quote. So we actually read through that glossary of Ethereum, and we must say that it's actually pretty good. I would rate it as a very proficient junior developer in Ethereum. And the question is, do you think it will take, or if or when will actual ChatGPT or OpenAI be as efficient that it can write smart contracts instead of people and make zero mistakes?
Just a bit of a background story on that. We have a lot of like newcomers to Scroll that are not from crypto background, so a lot of them are not familiar with a lot of terminology. So at some point I was like, yeah, I just need to create a glossary that explains everything. And then a few days later, ChatGPT was released. And I was like, yeah, why should I do the work if ChatGPT can do the work for me? So I played around with it, and I was like, yeah, I'm not really happy with the results. So I think my job is safe for now, because ChatGPT has a cutoff of late 2021, and a lot of new discussions about rollups came around in 2022, and especially another problem with ChatGPT is just it doesn't. At least I don't think it like learns from Twitter threads and stuff. And with rollups, most of the discussions are on Twitter. So if you don't follow Twitter, you won't know how rollups work. And so it doesn't really know what rollups are and doesn't really understand how they work. So my job is safe for now. When it comes to smart contracts, I think eventually we'll get to the point where it's going to be proficient at doing that. But yeah, I'm not. I'm still a bit skeptical on whether like you could just say, oh yeah, just write a contract that emulates a certain thing, and they will just come up with the way to write it. But again, I'm not really an AI researcher, and my only experience with AI was basically using ChatGPT and other other stuff like that. So yeah, it's difficult for me to answer, but I can. It's definitely a possibility.
I also asked ChatGPT to generate 10 questions to the Python job interview, and the questions was really perfect. This is exactly the thing that I want to ask to people who want to be a Python developer. And when I read the answer to these questions, I mean like 9 of these questions, 9 of these answers, it was okay. It was like acceptable. It was like more than acceptable. One thing was really stupid, but it was only one question. So for now, I think the junior developers should be scary, really. They should be scary because these things understand the simple construction of the different programming language much better than any human at all, in my opinion.
Does it do solidity as well? Sorry, I haven't really looked into that part. Does it do solidity as well?
No, I didn't do these things with Solidity, but I think I will do the same experience because this is a great idea. Thanks. And I think, Paulina, do you want to ask the last questions about layer 3?
All right, that's that one. Do you think that there will ever be a layer 3, like nested rollups within rollups, and so on? Yes?
No. Wait. Come on. In our notions, it was formulated in the way, is layer 3 bullshit?
I actually have this because I was on a research call with a few of our researchers a couple of weeks ago, and half of the people were like, "What's the point of L3s?" And I was like, "Yeah, okay, I'll just write an article about it." So now I'm working on an internal piece explaining why L3s are necessary.
So you don't think that it's vaporwave? You think it's useful things?
I think definitely. So I'll give you my reasoning for that. So one, doesn't matter how much you improve your EVM-based protocol, you're always going to have some bottlenecks related to how the state tree grows or execution. So, for example, you can't really parallelize EVM at this point. There are a few ways you could achieve some parallelization, but there are still going to be some bottlenecks there. And so you are fundamentally limited by certain things in the number of TPS you can do per instance. And at that point, and also bear in mind, a lot of applications don't need composability. So for example, if you're doing games or if you're doing like NFT trading, you don't need instant composability between different applications. And essentially what that allows you to do is segregate, because as a user, let's say if I'm paying for shared space on Ethereum, I'm competing with everyone. I'm competing with DeFi users. I'm competing with NFT people. I'm competing with MEV people. I'm competing with everyone. Whereas if I use my own space that is segregated and I don't really need composability, it's perfectly fine, and it's going to be much cheaper for me to use because I'm not competing with everyone. I'm just competing with the people who are also using that application. And so I essentially see the world where all the current L2s will become their own hubs within the ecosystems. So let's say ZkSync will be the hub to their own ecosystem of L3s. Starknet is going to be hub to the ecosystem of L3s. Same with Scrolls, same with everyone. Where the L2 is going to be used for composability of L3s, and L3s are going to be used for a lot of applications that don't require frequent composability. So games, certain DeFi apps that are not really composable, certain other things like again NFT trading or stuff along those lines. Because I just don't see a reason why you would put it all on one L2 and just call it quits. And composing through L1 is going to be super expensive, so you might as well do it through an L2. Because I hear a lot of times people are, when I discuss this stuff, they're like, yeah, but why don't you just deploy another L2 versus deploying it as an L3? But the argument is that, especially for ZK-rollups, you get amortized cost in terms of verification because you can recursively verify all the proofs and compress them into one proof. Whereas if you all post into an L1, you all spend the same amount of money. And on top of that, you are composing with an L1 through an L1 to other L2s. And I just don't think in the future L1 is going to have a lot of users. In a sense that individual users, the main users of Ethereum are going to be rollups. And and people who do arbitrage between different chains and stuff like that, and or liquidity providers. And so there's not a lot of reason to be composable directly with an L1, unless you're doing one of those things.
I think we will finish. Okay. You know that a few weeks ago, the Kherson, it's a big city of southern Ukraine, was liberated. One of the important reasons why it was happened, because not only democratic countries give some weapon to the Ukraine, but because a lot of individuals help Ukraine to buy weapons. So you can do it by donating crypto to the fund Save Lives, savelives.in.ua/donate-in. This is the URL where you can donate crypto to the one of the biggest fund who supports Ukraine.
Yeah, we're from Ukraine, and we actually had to postpone this episode for about 2 weeks because I was in Ukraine for these 2 weeks, and it's very hard to find a place where both electricity, internet, and heating works. And that's all because Russia is a terrorist state who think it's alright to bomb infrastructure of Ukraine. But luckily, because of donations in democratic countries, we have the air protection systems. I forgot the English name for it. I'm sorry. So yeah, please donate. And this podcast is available at YouTube, Spotify, Apple Podcast, Google Podcasts, Spotify again, Amazon Music. Also join our Twitter or follow us at Telegram. Please subscribe whenever you can. If you think the podcast is good, put a thumbs up. If you think the podcast is bad, please comment and tell us what is wrong, or just directly reach out to us in all of the platforms above. Thanks for listening, tuning in. Thanks to Toghrul for joining us for this episode. And bye!
Thanks for having me. Bye.